Am I audible to everyone?
Yes, sir.
So give me a number.
Binary number.
No, decimal number.
अच्छा, decimal.
Any decimal number. Tell me, and we'll show how to convert it in the IEEE 754 32 or 64-bit system. Any number, whatever in your mind. যা হবে একটা দাও।
2222
2222 and point দেবে কিছু?
22.22.
22.22. That's the number. Okay. So, and we will convert it in the binary format. So first of all, what you have to do? First convert it to the binary form. I think all of you know how to convert it to the binary form. First take the this portion. So you can take a negative sign also here, and it will be better, I think, so that we can give the sign also there. So now just take this 2222 and convert it to the binary form. So divide by 2, it will be 1 1 1 1, and you will get 0 here, and 2, then you will get 1 na, then 2, 2, then 1, $17, that is the system na. Okay, so that means 2022 is actually 100010101110. Just check it once. Then what is the binary presentations of 0.22? So multiply it by 2, you will get 0.44, that means 0. Then again 0.44 into 2, 0.88, 0. Then 0.88 into 2, then it is equal to 172, 176 na, 0.76, it will be 1, 0.76 into 2, and in this way actually you have to go for, and you have chosen a numbers which will not recur. That means you have to calculate at least 23 such digits, without which you can't actually express your numbers, because in this Mantissa I think there will be unique numbers. All numbers are actually what? Unique. So now help me to calculate all these values, because we need all these numbers. So now just one by one, and first two digits are 0, so that means, but here you have total 1 0 0 0 1 2 3 4 5 6 7 8 9 10 11 12 numbers, and that means after that 12 or 13 numbers are sufficient for this. So then 0.76 into 2, after that you will get 1.52, that means 1. Then 0.52 into 2, that means you will get 1.04, that means it is 1. Then 0.04 into 2, 0.08, 0, 0.08 into 2, 0.16, 0, 0.16 into 2, 0.320, 0.32 into 2 is equal to 0.640, 0.64 into 2, that means 1.28 G and 1, this is 1, then 0.28, into 2, 0.56, 0, 0.56 into 2 is equal to 1.12, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think some more digits we need. 1.1, 0.12 into 2, 0.24, 0, 0.24 into 2, 0.48, 0, 0.48 into 2 is equal to 0.96, 0, and 0.96 into 2, that means it will be, after that you will get some 1 values, so 1.92, and you will get 1, and it will continue. So that's a large number, no, actually a non-recurring number, and that's why we are getting this type of figures. So now express the numbers first in the binary form. That means your minus 2222.22 and 2, this is 10 decimal numbers, is actually 0, then 1, not 0, this is 1 0, 1 triple 0, 1 0, 1 0. হ্যাঁ
বলছিলাম যদি নন রিকার্সিভ হয় তাহলে 23 বিট অবধি আমাদের ক্যালকুলেট করে নিতে
না,
হবে।
23 লাগবে না, সেটা বুঝতে পারবে এবার কেন বলছি 23 লাগবে না। এখানে কতটা আছে দেখো, এই লাইনটা লেখার পর বুঝতে পারবে, আমি বলে দিচ্ছি 23 লাগবে না কেন। সো 1 0 0, তো এখানে ফার্স্ট কতগুলো বিট এসছে দেখো, ইন দ্য পজিটিভ পোর্শনস অ্যাকচুয়ালি বিফোর দ্য ডেসিমাল পোর্শন ইউ হ্যাভ 1 2 3 4 5 6 7 8 9 10 11 12, total 12 number, 1 2 3 4 5 6 7 8 9 10 11 12, 12 means আমার টোটাল 23 লাগবে। That means if you take 1 in the left side in the normalized form, so after that 11 usable, তার মানে only 12 ডিজিট হলেই বাকিটা হয়ে যাবে, সেটা দেখতে হবে। পয়েন্ট, দেন এবার এগুলোকে বসিয়ে দিচ্ছি পরপর দেখো। দ্যাট ইজ দ্য সেকেন্ড পোর্শনস হুইচ ইজ 0 0 1 1 1 0 0 0 0 1 0 1 0 0 0 1, then dot 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 is running. Now the second work is making it normalized. এটা হচ্ছে আরেকটা কাজ, একে নরমালাইজড করতে হবে। সো ইউ টু মেক ইট নরমালাইজড ইউ হ্যাভ টু শিফট দ্য পয়েন্ট ফ্রম হেয়ার টু হেয়ার, এখানে নিয়ে আসতে হবে পয়েন্টটাকে। কতগুলো আসতে হবে দেখো, 1 2 3 4 5 6 7 8 9 10 11, so total 11 actually point positions you have to shift. So that means it is 1 point, তাহলে এবার দেখো এই পয়েন্টগুলো তাহলে এর সাথে ইউজ হয়ে গেল, তাই তো, মেনটির সাথে। Is it clear that in the before left sided portion these numbers are also used in the Mantissa part after making it normalized. That means this 0 0 0 1 0 1 0 1 1 1 0, now these 11 numbers with that portion, with after the point portion, it will make the Mantissa. তার মানে শুধুমাত্র এই পোর্শনটা Mantissa করবে না। So that's why we don't need the 32 actually digits from the point portions or the decimal portion. 32 আমার total 23 লাগছে না, we don't need the 23 number digits, we need only the 11 plus x numbers from these portions. তাই এখান থেকে বললাম 12-13টা sufficient. So now if this is 0 0 1 1 1 0 and 0 0 0 1 0 1 0 0 0 1 dot 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 into 2 to the power 11, na? Is it okay? We have shifted the point in the left hand side, so that's why it will be 2 to the power 11. Now what is the Mantissa that you will shift? So you will save total 23 points for the Mantissa, and which will start from there, this point, not this one, because in IEEE 754 it default it have 1 point. So you will start from that 0. So it will be 0 0 0, then 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23. So here we will cut the numbers in that positions, we will cut it. So for Mantissa we will take these portions in the mantissa, that portions for the mantissa. And for the exponent we need this 11. This is not 1 1, okay, this is 11. So by coincidence we have also 11 just looks like a binary number, but this 11's now in the decimal form, this 11 in the decimal form. So that's why we have to convert it to the binary form for saving. But before converting it, you have to make it a biased by adding 127, because here it is positive, it is okay, but IEEE 754 format always use the biased exponent form. So that's why this is the exponent. So here the exponent is equal to 11, but in 32-bit system this biased exponent is equal to 11 plus 127, 718 to 13, that means 138. That is the biased exponent. Now make it binary. Now 138 divided by 2, 0 2 1 17 0 1 0 0 0 1. So that is the number here, 1 2 3 4 5 6 7 8, and you have 8 space already there, and you can fill it here, and you will never get more than 8 numbers here, because it ranges always belongs to that. So that's why this 138, which is the decimal values biased exponent in the binary form, it is 10001010, that is the binary number. So now it will be saved in the exponent portions. So that means this minus is stored with the binary digit 1. So corresponding to this minus sign, you will get the binary digit 1. Then that is the mantissa. This is the exponent portion, 1000 1010, and this is the 32-bit mantissa. Now if it is a 64-bit system, that means you need more values here. So you have to calculate more and more, and you need more values because there are total 52 space there, and it will be very difficult, obviously. Not for calculation, it will be laborious. So that means now your 2222.22, this number, if you save it, so its first sign bit will save here 1, and after that total 8 bits are there, and in this 8 bit 1 2 3 4 5 6 7, here you will get 1 000 1 0 1 0, and after that total you have 23 bits there, and in this 23 bits you have to save all the mantissa values, and if you save it here, so you will get 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 23. I don't know how many total digits are there, but we can start saving that. So it will be 0 0 0 1 0 1, then 0 1 1 1, and then 0 0, after that 1 1, then 4 zeros are there, then 1 0 1. So that's the number in the 23-bit system. So first we'll cover it, box it here like that. Okay, so that's the number. So it is the number, and how it will save in your 32-bit machine. This 2222.22, this number will save like this. So obviously it will neglect some values. So that's why if you have a 64-bit machines, your calculation will be more accurate than the 32-bit machine. So that's why for the space research or anything else we need the supercomputers, because it can hold more precision values. If your machine have a less precision values, then it will gives you the less precise data. But if your machine have a more precision, then it will give you more precise values, because it can hold the digits, holds the numbers. Otherwise in the calculation, in every step it will just cut the values, just chop the values, and in this way your accuracy will actually compromise. Is it clear? How to save the data?
Yes, sir.
Okay. So next, in your there is another term which is called the machine epsilon. That is very important. Machine epsilon actually just give you the how precise your machine is. That's actually the machine epsilon gives. So that is another important term, machine epsilon. So this epsilon is very familiar to all of you. Epsilon means the small values, very small. So it means actually the how small values can a computer actually saved. That means this machine epsilon, if you want to define it, it is the gap from in between the number 1. Suppose the machine saved the number 1, then what is the just next number? So if your machine have a high precision, then after the 1 it will save that type of number 0 0 0 0 0, then large number of 0, and after that what? 1. If your machine have a high precision values. But if your machine have a less precision values, then it will just save 1, and after that 1 point, suppose 0 0 0 1. Now you can see that which machines can take more values or accurate values. Obviously the first machine, because it can actually store a small changes of the values, but it can't actually sense that, or it can't store that values. So that's why a machine epsilon is actually the gap between the 1 and the value just after that. So suppose if your binary machine after the 1 saves this number, that means the difference from this 1 to that number, this is the machine epsilon. That means the gap in between the numbers. So if this gaps is reduced, that means your machine is more precise because it can hold very small values also. Otherwise your machine will chop that values and it will store only up to that terms. Whatever maybe after that it will chop the values. If your machines just take the 4 mantissa, so after the 4 mantissa it will just neglect all the values, or it will just cut or chop that values. So that's why if we formally define the machine epsilon, what is the machine epsilon? So machine epsilon is the machine epsilon, which is denoted by epsilon m, is defined as the gap between 1 and the next bigger number. Okay. Suppose in 32-bit machine, so you all know that how the 1 actually expressed as. So how 1 actually looks like? So 1, this number is equal to 1 into 2 to the power what? Nothing is there. So that means if you put here only 1, so it will be 1.000000, this type of value it will get. Or in the 32-bit system, you all know that in the mantissa format will be 1.00000000, and how many zeros will be there? How many? Total 22 zeros, na? And after that you will get 1, not 0. Mane total here 23 actually zeros, because in the 32-bit system we save 23-bit mantissa, and in 23-bit mantissa we will save after that point, so starting from that 0. So in the 1 actually it save all the zeros, so total 23 zeros are there. If we can write it, it will be better, that 23 number of 0. That means 1 actually looks like 1.1 2 3 4 5 6 9 10 11 12 10 16 17 into 23. That is the number. That 23 zeros will be saved in the mantissa portions. And what is the just next number after that? That means the 1 plus epsilon m, that is the next number. Just after the 1, it will be the number. And what is the number? It will be 1.00. So the same number of zeros will be there, and after that at the end you will get 1 na. Is it clear? देखो तो এটা, that after the 1 what is the bigger number? Is it clear or not?
Yes, sir.
So then what will be the difference between them? So difference will be the epsilon m. That means just subtract 1 from there, and what you will get? You will get 0 point this 20 number of 22 number of zeros, 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22, and after that you will get 1 23. So if you express it in the exponent type of form, it will get actually 2 to the power minus what? 23 na? That is the number. So that means in a 32-bit machines, actually your machine epsilon is 2 to the power minus 23. So the total number of space allocated for the mantissa. So in 64-bit machine, if you take, in that case your machine epsilon will be what? Can anyone say what is the machine epsilon? 2 to the power minus what? What value will be there? Just remember
52.
52, exactly. Just remember the 64-bit format, because you have here 52 bits reserved for the mantissa portions. That means it can save this type of number 0 0 0 0, total 51 number of zeros, and after that it will have 1. So that's why the machine epsilon in a 64-bit system is 2 to the power minus 52, and it is smaller than that na. So that means this 64-bit machine can sense very small changes. If you take only 8-bit machine, in that case you have a very less precision. So if you take a 32-bit machines or 64-bit machines, you have a high precision values. So that is machine epsilon. So machine epsilon is the gap between the 1 and the number just after the 1. So the gap between them, and if this gap is smaller, then your machine have a large precision values, and if this gap is not very much small, this gap is actually larger, that means your machine is less accurate or less precise, gives you the less precise values. Okay, so now we will discuss one questions, and that means which cans or this type of questions may occur in your exams, and this type of questions are also very much important. So I am just showing the pictures here, because in 32-bit systems or 64-bit system, expressing the numbers and then saving it not very much useful. It is a problem from your practice set, and here you can see the particular systems for the normalized mantissa is already given. Particular system is already given, and just read out the problem first. Here it is says that the assume you have a base 2 computer, that means a binary computer, that store floating point numbers using 8 digits, that means 8-bit normalized mantissa. So that means the format is actually x dot xxxs. So it have a 8-bit total, so 1 bit before the dot, before the decimal point, and 7 bit in the right hand side, and a 6-digit exponent. That means 6-digit exponent means, again you can just assume it as x x x x x and x. That is a 6-digit exponent. Total 6 space will be there, or 6 box, and a sign for each case. So here it is says that the mantissa have also a sign for each case, not like the 754 format. So here the mantissa portions and also the exponent portion both have a sign. So in the mantissa also you don't have to save only after the decimal, you can save the point before the decimal also, but in the normalized form. So it is a particular type of machines where the machine formats are already given. Now for this machine, what is the machine epsilon? That is the first question. What is the smallest positive normalized number that can be represented exactly in this machine? That means what is the smallest positive numbers produced by that machines. And third is the if this type of decimal numbers are given in that machines 1015.1, then what is the mantissa and exponent stored by the machines. Okay. Here base 10 indicates the decimal number systems, not anything else. So first of all, so in this system, 1 represented as, if you take the 1 number, it will be represented as 1 point, then 1 0 0 0 3 0 4 5 6 and 7 na? Because here you can see that total 7 number of actually space is there for filling. So 1 point, then 7 number of zeros are there. Then the next number after the 1, which is 1 plus the machine epsilon in, it will be 1.00000060, and after that what? 1. Na? So what will be the epsilon m then? 0.000000 and 1. That is the number. That means in the binary system, in the decimal system, if we express it, it will be some or binary whatever. So 2 to the power what? 1 into 2 to the power 1 2 3 4 5 6 7 na? Minus 7. Is it correct, or is there any doubt? I think no doubt is there. So then we go to question number 2. So that is the answer. So it is your machine epsilon. You don't need to convert it to the decimal because it is already decimals number, because it is 1 into 2 to the power minus 7. Just calculate the 2 to the power minus 7 and you will get the values. So that means 1 by some values will be there. That means 1 by 2 to the power 7, and that is a very small values obviously. Now question number 2, what is the smallest positive normalized number? So you have to calculate the positive normalized number. So the smallest positive mantissa is smallest positive normalized mantissa is 1.000000 na? That is the smallest positive normalized mantissa, because you have a normalized mantissa. So if you take any one in the right hand side, so it will be bigger than 1. So the smallest positive normalized mantissa is 1.7 number of 0. Now you want to make it smaller than that, then you have to take a product with 2 to the power some negative values na? Because if you multiply it by 2 to the power some negative values, so it will be reduced, because multiplying by 2 to the power negative, that means divide by 2 to the power positive na? Because if you take 2 to the power suppose 100 here, so it means actually divide it by 2 to the power 100. So that means if you take a large number here, so it will gives you the smaller number or the smallest number. So just take the largest here, take the largest number here, largest exponent, and with the negative sign, then you will get the smallest positive normalized mantissa. Because if you take the 2 to the power 0 here, so obviously you will get the 1, and it will be bigger than if you take 2 to the power minus 20 128, because it means 1 divided by 2 to the power 128. So that means we will use the largest exponent here. So what is the largest exponent then in that machine? 1.0000, then 000 into 2 to the power minus of 11111, because in the exponents you can save total 6 number of digits, and we will save it all by 1. Now just express it in the decimal form and you will get your values. So what will be the in the decimal form, what is the value of that? So corresponding to 1 you will get 2 to the power 0, then corresponding to 1 you will get 2 to the power 1, then 2 to the power 2, then 2 to the power 3, then 2 to the power 4, and then 2 to the power 5. 32, then 16, 8, 4, then 2, and then 1. 3, 4, 7, 8, 7, 15, 15, 6, 21, and 2, 2332 21336. That means 2 to the power minus 63 in the decimal values. Now tell me, is there any problem or doubt?
No, sir.
So you may get some different format machines. Maybe there are total 9 numbers of space, or maybe 5 number of space there, or here maybe a exponent with suppose 5-digit exponent or 4-digit exponent or 7-digit exponents. So just you have to change it according to your questions. So that means here this is the smallest positive normalized mantissa and this is the largest exponent, and which will gives you the smallest positive normalized number made by that machine. So now the number 3, this third questions we have already did it for the IEEE 754 format. Now we will just do it for this particular type of format, but without any biased exponent, because here you don't have to take the 127 or anything sum, because here they are allowed for the sign also for the exponent part. So that's why here just we will export the 1015.1 from the decimal to the binary. 1015.1 10. So this is the decimal number, make it binary. So 1015 to 0 1 1 1 0 1 So that is the number, and then 0.10 0.10 into 2 0.20 0.2 into 2 0.40 0.4 into 2 0.80 0.8 into 2 is equal to 1.60 and not 0, this is 1. Then 0.6 into 2 1.21 0.2 into 2 it will be again 0.4. now it is going to the recurring process, so then 0.4 into 2 it will be 0.8. now this is 0, so it will continue like that. So that means your 1015.10 10, that is equal to 111111.0001100, and this way it will continue. So now just you have to make it normalized, so shift that point from here to here, 1 2 3 4 5 6 7 8 9 point, that means 1 point 1 1 1 1 1 0 1 1 1 0 0 0 1 1 0 0 into 2 to the power 9. That is the format. That means here your mantissa is, so the required mantissa is equal to, so it will take only the 1 and 7 digit after that point, 1 2 3 4 5 6 and 7. so just cut it from here. So and then it is 2 to the power what, 9. So that means, so what is the 2 to the power, just make it again. So required mantissa is equal to 1.1111101 and exponent, and with the sign obviously, so just take one positive sign here. So here you have to use the 0 or 1 because nothing such type of thing is given here, but since you have a base 2 computers, they have already set the stored floating point number. So if you want to use the 0 sign here, you can use it, so no problem is there, but just save it like that, that is the portions, and after that the sign bit save it with 0, that means the positive sign, while 0 represent the positive sign, 0 corresponding to the positive sign, and mention that. And in the exponent format, actually you will use that, just this is 9, so 2 4 2 1 2 2 0 2 1 0 2 0 1, so it is 1 0 0 1, but your actually space allocated here is a 6 point, so you have to put 2 0 before that number. So the exponent save will be also in the positive sign, so 0 for the sign bit, and after the 6 bit for the exponent values, so 0 0 1 0 0 1, so that is the value. No, this is so 6 bit and 1 for the sign, so that is the mantissa and exponent stored by the machines for this 1015.1. so this is a particular type of machine, so format is given in the question, but if only the IEEE format is said in the questions, so then you have to use the previous methods with the biased exponent and with 23 or 52 numbers of mantissa. Okay.